Have you ever looked up at the sky on a warm afternoon and noticed that many clouds seem to have a perfectly flat bottom, almost like someone sliced them cleanly with a giant invisible knife? From the ground, they can look like fluffy mountains sitting on a smooth, level shelf in the sky. It's such a common sight that most of us hardly question it. But when you pause and really notice it, the shape feels strangely precise for something formed by swirling air and drifting water droplets. Why would something as chaotic as a cloud end up with such a neat, flat underside? Today we will uncover the hidden atmospheric boundary that quietly shapes the bottoms of clouds, right here on History of Simple Things. To understand why clouds often have flat bottoms, we first need to think about what clouds actually are. Despite how solid they sometimes look, clouds are not fluffy objects you could stand on. They are enormous collections of tiny water droplets or ice crystals floating in the air. Each droplet forms when water vapor in the atmosphere cools and condenses around microscopic particles like dust, pollen, sea salt, or even pollution. These tiny particles, known as condensation nuclei, give water vapor something to cling to as it transforms from an invisible gas into visible droplets. But water vapor doesn't condense just anywhere in the sky. For clouds to form, the air needs to cool enough for that vapor to reach what scientists call the dew point. The dew point is the temperature at which air becomes fully saturated with moisture. Once the air cools to this point, the excess water vapor begins condensing into droplets, and a cloud becomes visible. Now here's where the flat bottom comes in. Near the surface of the Earth, the air is usually warmer. Warm air can hold more water vapor than cold air, which means moisture can remain invisible even when there's a lot of it. As that warm, moist air rises, however, it begins to expand and cool. This happens because air pressure decreases with altitude, allowing the rising air to spread out. When air expands, its temperature drops. At a certain altitude, that rising air cools enough to reach the dew point. Suddenly, water vapor begins condensing into droplets. And because this temperature threshold occurs at roughly the same height for the surrounding air mass, cloud droplets start forming across a wide horizontal layer of the atmosphere. That layer becomes the base of the cloud. Everything below that level is still too warm for condensation, so the air remains clear. Everything above it contains droplets that make the cloud visible. From the ground, this sharp transition creates the appearance of a clean, flat underside. Meteorologists call this level the lifting condensation level, often abbreviated as LCL. It marks the height where rising air first becomes saturated. Since large areas of air can share similar temperature and humidity conditions, the LCL tends to be fairly uniform across a region. That's why many clouds appear to sit on the same invisible platform in the sky. If you've ever watched a field of puffy clouds drifting across a blue sky, you may have noticed that their bottoms often line up at nearly the same height. These are usually cumulus clouds, the classic cotton ball clouds associated with fair weather. Each individual cloud forms from a small column of rising warm air called a thermal. As these thermals rise and cool, they reach the condensation level and begin forming visible droplets at almost the same altitude. The result is a sky filled with clouds that all seem to share a common flat base, even though their tops billow upward in wildly different shapes. The tops of clouds, by contrast, often look rounded, lumpy, or towering. That's because above the condensation level, the rising air continues moving upward and mixing with surrounding air currents. Turbulence, wind shear, and temperature differences sculpt the upper portions of clouds into complex shapes. Without a single boundary stopping them, their tops grow more chaotic and uneven. In a way, The flat bottom of a cloud is like the foundation of a building. It marks the point where the invisible ingredients of a cloud finally become visible. Interestingly, the height of this cloud base can tell meteorologists quite a lot about the atmosphere. On humid days, when the air near the ground already contains plenty of moisture, the dew point is reached quickly as air rises. That means clouds can begin forming at lower altitudes, sometimes only a few hundred meters above the ground. On drier days, however, the rising air must travel much farther before cooling enough to reach saturation. As a result, clouds form much higher in the sky. Pilots, glider enthusiasts, and meteorologists often estimate humidity conditions simply by observing how high cloud bases appear. This same principle explains why deserts often have very high cloud bases. The dry air near the ground means rising air must climb a long distance before condensation begins. When clouds finally do form, their bases can be several kilometers above the surface. Another interesting detail is that the flatness of a cloud base isn't always perfect. If the air's temperature or humidity varies across a region, the condensation level may shift slightly up or down. This can make the bottom of a cloud look uneven or layered rather than perfectly straight. You might also notice that some types of clouds don't have a clearly flat bottom at all. For example, thin, high-altitude clouds like cirrus often appear wispy and irregular. That's because they form in very different conditions, typically at much higher altitudes where ice crystals dominate and atmospheric dynamics behave differently. Storm clouds can also appear less tidy. In towering thunderheads, known as cumulonimbus clouds, the base may still start relatively flat, but powerful updrafts and downdrafts can distort the structure as the storm intensifies. Sometimes the flat base of a storm cloud becomes darker and more dramatic. This happens because the cloud grows thick enough to block sunlight, casting shadows within the cloud itself. The bottom may look heavy and ominous, even though the same condensation boundary still plays a role in shaping it. So the next time you look up and see a row of clouds floating across the afternoon sky, with their bottoms neatly flattened, you're actually witnessing a boundary in the atmosphere itself. It's the exact height where warm, rising air cools just enough for moisture to turn into tiny droplets suspended in the air. In other words, that smooth underside isn't random at all. It's the visible signature of physics happening all around us, an atmospheric threshold that clouds cannot form below. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution. Thank you for joining us on this journey through the history of simple things. Don't forget to like, subscribe, and stay tuned for more stories woven through the smallest details.